Hi guys, after discussing the continuous time and discrete time signals, I want to focus on two very important signal types. These are exponential signals and sinusoidal signals. If you look at the slide right now, you can see that in this course, in this subcomponent, we will be talking about complex exponential signals very often. When we talk about Fourier transform, Z transform, Laplace transform, we are always talking about actually complex exponential signals, okay? In high school and in other courses in calculus or something like that, we are used to seeing real exponential signals like 2 times e to the power minus t, 1 over 2 times e to the power t over 2. We are already used to seeing all these kind of signals. These are called real exponential signals, okay? For example, this one is exponential growth. This one is exponential growth, as you see here. This is like an exponential decay, which is this one, right? Like the capacitance, the decay of the population or the discharge of a capacitor can be seen in exponential decay as exponential decay functions. For example, in population growth, you can see exponential growth, or capacitance charging, you can see exponential growth in those kind of real world problems, okay? So first thing, it's easy. If we are seeing these kind of signals, we should always be putting some t values. If t is equal to 0, e to the power 0 is 1. If we put e to the power minus 2, which means like 1 over e square, which will be slower. And then if you put t as equal to 1, 4, this will be like e to the power 4, and it will decay like that, okay? If you put 2 here, e to the power 1. If you put 4, e to the power 2. If you put 8, this will be e to the power 4. So this will be increasing as we increase t. So I hope you remember all these things. It's very easy if you think about real exponential signals. Let's start talking about complex exponential signals. This is something new for you, and you haven't discussed this in other subcomponents or courses that you have taken so far. So this is critical that you understand this part, arkadaşlar. So first I will start with purely imaginary complex exponential signals. Okay, this part will be like purely imaginary, okay? Like e to the power j omega 0 t. So this is my scalar. C is my scalar. Okay, 2, 1, 1.6, minus 3, those kind of values. Let us focus on this part, okay? So maybe you remember from Euler's description or Euler's relationship. When we think about e to the power j omega 0 t, it is equal to cosine omega 0 t plus j sine omega 0 t, okay? J is our complex variable, like j square is equal to minus 1, if you remember from complex algebra. And this omega 0 will be our, like we will call it angular frequency, okay? Angular frequency, açısal frekans. So you know we have f, which is like our frequency, omega 0 or f0 and omega 0. This is angular frequency, and this is regular frequency that we have. So I hope you understand this Euler's relationship, or you remember Euler's relationship. This is a periodic signal, because if you, what was the periodicity definition? X of t should be equal to x of t plus capital T. This is our period, okay? If you remember in the previous parts of this subcomponent or course, you will see this periodicity will like when a signal is periodic, then this signal will repeat itself at every t seconds when t is our period, okay? So let me like prove that this is a periodic signal. If I put j omega 0 t plus t, what should be the output? It should the output should be equal to the a e to the power j omega 0 t. Okay, if these are equal to each other, then that means the signal is periodic with t. So if I put omega cos omega 0 t plus t, capital T, j sine omega 0 t plus capital T. So if you think about this like cosine, let me draw a cosine signal here. Okay, this is my cosine signal, and this will be my period. Okay, this is my period, this is 0, this is t. If you think about, this is my, let's say t is equal to something, t plus t is going to be here. So this cosine omega 0 t plus t is equal to cosine omega 0 t. Okay, because cosine omega 0 is periodic, after t seconds, it will repeat itself and it will come to the same point. Same thing for sine waves, okay? Sine wave is something like this. And then like this will be my period. This is t. Let's say this is x of t. This is x of t plus capital T. So again, sine omega 0 t is periodic. So omega 0 t plus t will be equal to sine omega 0 t. So what do I say here? This this complex exponential signal is a periodic signal, and its periodicity is t, and its angular frequency is omega 0. Okay, let me remind you one thing. Omega 0 is equal to 2 pi f0. Okay, this is my fundamental frequency, and this is going to be my fundamental angular frequency. Okay, so omega 0 is equal to 2 pi f0. I think you should remember this. This is a very critical thing. And if you remember, f is equal to 1 over t. Okay? So if my signal is repeating itself every 1 second, okay, then I would say my t is 1, my f is 1 hertz. Okay? If my period is 1 second, my frequency is 1 hertz. If my period is let's say, if my period is 2 seconds, that means this is 2, this is 4, that means f is going to be equal to 1 over 2 hertz. What does it mean? The definition of frequency is the number of times that a signal repeats itself in 1 second. This is the definition of frequency. The number of times a signal completes its one period in 1 second. Okay, so because in 1 second it only comes to here, like it can complete half of the whole signal. That's why it's called 1 over 2 hertz. If t is equal to 1 over 2, that means this is 1 over 2, then it will complete the cycle twice, right? So it will be half second here, 1 second here. How many times did I complete a cycle? 2 times. That means it will be 2 hertz. So the number of times that a sine wave or a periodic signal will complete its cycle in 1 second will give me the frequency. So this will be my frequency, and like this is like 1 over f. We should remember this these formulations as we go further. Okay, let me remind you again. Omega 0 is equal to 2 pi f0. Like angular frequency is something like this, arkadaşlar. It will go around a unit circle like this. Okay, like this is my omega. Like if you remember from the angular frequency of a moving object, like this will be my angular frequency, this will be my angle, and the number of times that I turn around this unit circle, birim çember, the number of times that I'm moving around this unit circle will give me the fundamental angular frequency. Okay, the number of times that I do this every second will give me the frequency. So arkadaşlar, I hope you remember or you understand what is a complex exponential. Let me write again. My signal will be like equal to c to the power at. The first part is like both c and a are real, then it will be real exponential signals like these. If c is real, but a is a complex, purely imaginary complex number, like j omega 0, then it will be like, using Euler's relationship, it will be e to the power c times e to the power j omega 0 t, and it will be cosine omega 0 t plus j sine omega 0 t, okay? And it's a periodic signal, and my fundamental period will be t, my fundamental frequency will be equal to omega 0. So let us move to the sinusoidal signal, which is something, again, very critical for us as electrical engineers. We use sinusoidal signals. In Turkish, we call it sinüsümsü. Oidal means like something related to or something similar to sine waves, okay? So pure sine waves are like these. If I add two sine waves, it will be like sinusoidal signal. So here there's like cosine wave. I have a fundamental frequency, my time, my independent variable. This will be my phase shift, okay? My phase information, phase shift. Faz kayması, faz, okay? So normally for a sinusoidal signal, I have a cosine or a sine wave, and I have a, let's say, amplitude of my sine wave. This will be my amplitude, okay, A, and this is minus A. This will be my amplitude, and this is like a T, my signal. And omega 0 will be like difference between these two, 2 pi divided by T. This is going to be my T period, and this is going to be omega 0, okay? And then phi will be in radians. We call this phi, okay? We write it like this, phi. And it is in angles or in radians. And we will be talking about these like pi over 2, minus pi over 3, those kind of shifting or like a delay in my signal, okay? Like phase shift is a kind of, phase shift is a kind of delay in my signal, okay? It's a kind of delay in my signal. So I talked about these, and at home, I want you to draw this signal on your own. Cosine 2t plus pi over 3, what does it mean? When you put t 0, it's going to be like cosine 90 degrees. If you put something else, I want you to draw the signal at home like this as your time, but time will be in radians, okay? And then I want you to plot this cosine wave on your own, okay? So this is all for this part. In this video, I talked about like complex exponential signals, okay? Like c times e to the power at will be my signal. This a might be a pure imaginary or different types of signals, okay? And you will see these much more often, c times omega 0 t, and then maybe like times phi. This will be your signal. And then we also talked about a times cosine omega 0 t plus phi. This is my sinusoidal signal, and we will be dealing with these sinusoidal signals very often, okay? And the next video, I will be talking about calculation of power, energy concepts, and I hope you will understand those parts also. Let me remind you one other thing. This is not only for continuous time signals. It is also possible to have like c to the power j, like omega 0 n kind of thing, okay? Now omega 0 will be something different. For example, here I will have this kind of periodic signal, okay? And then like this is an exponential signal, for example, let's say minus 2 e to the power j minus j n. If we are trying to plot this signal, please go ahead and try to do it on your own. I want you to think about the same concepts in discrete time. Okay, so please work on the discrete time versions of the things that we talked about in complex exponentials and sinusoidal signals, because this is also possible at that point. Okay, this is all for this part, and we will move on with the energy and power calculations.